Thank you so much, Laura, for the introduction. And thanks all of you for being here. I was pretty scared. I got to speak at the ballroom at 5:30, right before everybody gets to go to a bar. So this is way better than the 5 people I was expecting. So that's pretty good. So my name is Puertas Calvo. As Laura said, I work for Microsoft. And today I'm going to talk about a new compromise detection system that we've been working on that uses behavior analytics. And I'll go and explain everything about that. But one of the important parts of it is the title says it's for compromise detection in real time. So let's start with that. What's the importance of real-time compromise prevention, and what does it mean? When we say real-time compromise prevention, we're talking about at authentication time. A user comes with a username and password and authenticates, and at that time we want to know what is the risk of that authentication of being compromised. We want to be able to block the authentication at that time if we think it's bad. Why is this? Well, there's a bunch of stats in here that a lot of you are probably already familiar with if you work in security or identity. We know that passwords are terrible. 81% of all breaches leverage stolen or weak passwords. We know also that we live in this new cloud mobile world in where a username and password sometimes is the only thing you need now to get into an organization's data. There's no more perimeters, there's no more firewalls. Everything is accessible just with that username and password. So we have to protect those authentications right when they're happening. Other scary numbers are about the speed of attackers and how stealthy they are when they actually breach an account. 2 hours or 158 minutes is the average time that it takes for an attacker to move laterally in the network once they're in, right? So offline detections are not good enough anymore. Because by the time we've detected, the user, maybe it's already done. They've already stolen everything they needed and they're gone. It only takes them 2 hours to move. Another number has also to do with when we actually detect these attacks. In the average time, it's estimated to be at 197 days, the mean time to identify that a breach happened. And the reason for this, there's probably a lot of reasons, like attackers are not trying to be identified, they're trying to gain persistence, but also we don't have enough resources and enough people looking into this data and trying to find these attacks. There's this shortage of 3 million people worldwide for security jobs, right? So we need to give organizations the ability to protect themselves in an automated way instead of having to depend on people finding these attacks way later. So now, how are we going to do this? How are we going to prevent these attacks? It's by making use of the adapted authentication framework. Who here has heard or understands what adapted authentication is? Okay, well, that's a good number. So I have a very short example of how a risk algorithm can be inserted into adapted auth. We have a username username and password, and then that information travels to the network and reaches our cloud detections. And then we have a risk engine that works at the time of that authentication. So before we've given the token to the user, there's this risk evaluation that happens. The engine will say, oh, this authentication was risky. Let's say this is medium risk. So now this is how we interact with the engine. The engine has a policy that says, oh, when a user comes with a medium risk sign-in, you have to make that user give you a second factor of authentication. So then the user is presented with an MFA challenge. And in that case, 2 things can happen, right? If we've actually challenged the real user should have access to their second factor, and they will pass the authentication, and then we'll give them a token, and everything will just go smoothly, and sorry, we were wrong. But if it was an actual attacker that had the password, this should have deflected the attack, and the attacker now is not able to get into the account. So effectively, this is how we're trying to prevent the compromise. And not only that, but we would also generate a risk event, and this is some kind of alert that will go into a SIEM system or a security dashboard, so some security operations can actually look into this and discover that this user account or the credentials were compromised, so they can go and remediate it. So now that we know how this risk engine works, it's also to understand that the risk engine can make mistakes. If it's actually the user, if it's me trying to log into my @Microsoft.com account, but maybe I'm traveling, I'm in DC this week, and maybe I use, I don't know, one of the computers from the AV people in the back to try to access my slides. Maybe that happens, and then the system thinks that my authentication is risky, in which case maybe the adapted engine blocks me or makes me do an MFA, and I didn't bring my phone with me. So that slows down productivity. And that's what we call a false positive. It also increases help desk costs, because we might be blocking real users when we think they're bad. And it also causes security analyst fatigue, because we're generating all these risk events and alerts that go into security products. And if we generate tons of false positives, the analysts are not going to have enough time to look at all of them, so they will just stop paying attention. And then there's the other kind of error that you could argue, for me as a security professional, is the worst error, is when we actually think that the compromised sign-in is good and we don't do anything about it. We just say it's not risky and we let the bad guy in the system. In this case, the attacker will go undetected and your organization will breach. Now, as I said, for me, clearly the second one, the false negative, is much worse than the other one. But you really need to strike the balance between the two if you want organizations to adapt this risk-based adaptive authentication, because if there's too much cost, if there's too much slowdown in productivity, then those identity admins are going to have other forces that are not letting them implement this type of friction in the users. So we define these customers or these organizations as the two edges are the risk-tolerant organization, and I talk to customers a lot, and there will be people telling me something like, your algorithm is too noisy, I cannot implement the risk-based MFA because I'm afraid that one day my CEO will have to solve an MFA and they just don't know how to do it. And then there's the risk-averse organization. This is the type of organization that actually has already suffered a breach. The risk-tolerant organization is the one that has suffered a breach, but they don't know about it yet. So the risk-averse organization, they say, oh, yeah, I had a compromised user, but you didn't detect it. Maybe this happened when the user was phished, and maybe the bad actor already knew the location and the user agent of the user, so they were able to get through the system, and the system did not detect it. So these organizations require different settings in order to say what risk they're able to tolerate. And finally, let's talk about finally in this intro, let's talk about the way we're going to do this. So behavior analytics, also show of hands again. Do people understand or have heard of what behavior analytics are? Oh, wow, that's a pretty impressive number. OK, so basically what we're trying to do here, this is a security modality of behavior analytics. We're just trying to see if when we see a new sign-in in the system, we're comparing it to what we know about the user and deciding if that sign-in looks like the user or looks like it's not the user. So the system will collect different attributes from the sign-in, and then we will compare it to what we have stored in the user activity database, and then the risk engine will make a decision. So what's the goal of this system then? We have said that we want to use behavior analytics to create a compromise detection, but also real-time, because it's extremely important to do it at the time of authentication so we can actually stop the bad guys. We have to make it highly accurate because we know that both the false positives and false negative errors are really bad, and we don't want to add friction to the users, and at the same time, we don't want to miss the attackers. But finally, we also have to make it flexible. We have to say that there's different risk confidence levels that can go into the adapted authentication engine, so organizations can set policies based on the risk level that they're comfortable with. So we didn't start this really from scratch. I mean, we did, but years ago. But this is kind of the system that we started with when we embarked on this project. We have, this is the adaptive auth engine, and the way the algorithm worked was really just very binary. So you can see in the blue box with code, if you can read that, it's just, we compare all the attributes of the sign-in with the past activity of the user, and if we find one thing that matches, and that could even be location, then we say that login is OK. It's fine, no risk. But if nothing matches whatsoever, then we say that that's medium risk. So there's no concept of that entity that's stored in the database. How many times have we seen it? How often? How long ago? Is it the same weight if I saw you in this IP every single day for the last 3 months than if I just saw you on this IP 3 months ago? Same for location, same for other things. And then there's also no concept of different risk levels. We're just treating every no match the same. It doesn't matter if you don't match, but you're 100 miles away, or if you don't match and you're 10,000 miles away. So that's kind of like the problem we're trying to improve upon. So how are we going to improve it? First, we're going to track more behaviors. Second, we're going to enhance this behavior analytics by introducing frequency and recency of the matches. Then we're going to implement an algorithm that takes all of this into account, the features that we're tracking or entities of the sign-in and all of these frequency patterns. And that's going to generate a match score. And with this match score, then we're going to define the risk confidence levels, and we're going to use a probabilistic approach to do that based on what is the likelihood of a user or a sign-in being a compromised one for each different match score. So let's start with more behavior structs. What are the things that we're looking at that to compare with the activity you had in the past? One is device identifiers. They're not easy to get. Not every single authentication will give you one. We have authentications that are native apps, webs, legacy authentication, email protocols, you name it. So not all of the features that we track are present in every signing, but we get as much as we can to make our algorithm the most accurate. IP address, that one is present in every single authentication because you cannot have communications on the internet without an IP address, right? Geographic location can come either from metadata that we get from where the IP address is located, or we could even put, if a device has GPS information that the user has consented to give us, we can also use that to figure out where the user is located geographically. Browser sessions, session cookies, they're super useful because they tell us if it's the same device, again, similar to device identifier. And then we have some other cool or useful information that we get either on the claim or because organizations can set up what their corporate networks are, then we can see if the user is coming from corporate network or not. Or we can even infer that by using algorithms because we see all the data from every single authentication that we see, so we can actually infer which IP address belongs to which tenant based on the traffic that we see from the different organizations. And then we can also do some cool things like aggregating IP addresses into IP networks, using subnets, et cetera. So that's the type of stuff that we're trying to match the behaviors on. And then we're enhancing the analytics by enhancing the things that we're actually tracking. We're just not tracking anymore, have I seen you in this IP before or not? But we're also looking at things like, how many times have I seen you in this IP address? What's the frequency of access? Is this a place that you log in from every day or every hour or once a month? The recency of access also matters. Were you in Thailand yesterday and you're in Thailand today? Or were you in Thailand yesterday and in Thailand 7 months ago? That doesn't have the same level of confidence, right? And then finally, there's also distance to known geolocations. So if we cannot really match much, for example, in legacy protocols that don't give us any device information, location becomes really important because IP address is basically the only feature we can match. And then from that, we can get the location. So the distance to the location you were yesterday is important because a login that is 5 miles away from when I last saw you, it's for sure less suspicious than if all of a sudden you log in from 10,000 miles away in 5 minutes. Right? So that's the better behavior analytics. And then with both the new entities that we're tracking and the behaviors, we're going to compute a match score. Now, this is a lot of math, so I'm going to spare it for you because it's 5:30 in the afternoon. But basically what we're trying to answer is on a scale of 0 to 1,000, that's just an arbitrary scale, how much does this sign-in look like the user's past behavior? How much does it look like you? So we do this by, I'm going to give you a little bit details of how this works. So in general, we're adding weights to the things that we're matching, right? So the more frequent and recent a pattern is, so the more weight it will add to the match score. So if you log in from an IP that you log in every day, that's going to have more weight than if you log in from an IP that maybe I've only seen you one time. The more unique the entity, also it adds more weight to the match score. And by unique, we mean how unique that thing is to a specific user. For example, this is very clear. A device, it's normally something that we only see for one user. There's only a one-to-one relationship. Normally, we don't see 2 or 3 users in the same device. So if I've seen you in this device before, that's going to have a very high weight. But a location, it's something that we see tons of users coming in from. Let's say the location is like this hotel here right now. There's like tons of you here logging in right now. So that would be a low weight to the match score because it could really be anyone. Anybody could have access to that location. And then lastly, we also have negative weights. We lower the score for things that don't match. So if you all of a sudden come from like a completely new device, that's going to remove some weight from the score. So once we've done this, we have all this match score. We have to select how we're going to map this to risk, right? So this chart here on the horizontal axis that has you can't probably see it, but it has numbers from 0 to 1,000. That is the match score. And then the y-axis, or the curve, is just the distribution of match scores for all the sign-ins that happen during a whole day of logins. You can see that there's some spikes in the middle. Those are normally happen for like the most frequent access patterns. And then the ones on the right will be the users that have features that most people don't have. Like let's say you have device identifier, corporate network, everything is perfect and everything aligns. But the stuff that we really care about is the little tail on the left, the very low match scores, the things that look really suspicious, things are not really matching. How are we going to map that into risk levels? So what we do is we take an experimental, empirical sample of known compromise sign-ins and known benign sign-ins, and that represents real life. And then we plot the balance between the two errors that we talked about at the beginning. So actually, my boss, Alex Reiner, just gave a much better description of an ROC curve that I'm going to give right now because he's a much better storyteller. But he called it the irritation curve. If you just went to his talk, you understand what this is. So the false positives on the horizontal axis represent how many good users will get annoyed. And the false negative on the vertical side will represent how many bad guys will get through you. So it's the two errors, right? So the key here is to say, okay, well, what's based on risk tolerance of the organizations, I can decide which risk levels I'm going to give them. And as you can see, there's always an inverse relationship between the false positives and the false negatives. So you have to figure out what's the balance, right? So for the risk-tolerant organization, this is the organization that definitely does not want to bother their good users. The false positive rate has to be low, so it has to be somewhere on the left, which means they're still going to miss some of the bad guys going through. For some medium risk, for some average organization, you will find like a balance that's never going to be perfect, but something between the false positives and false negatives. And then you have your risk-averse organization. That's the one that definitely doesn't want any bad guys coming through. So you want your false negatives to go real down and be really low, which means you'll have a higher level of noise and a higher level of user friction. So in summary, we're enhancing the behaviors that we're tracking. We have a much wider range of behaviors, and we weight them differently depending on the uniqueness. We have better behavior analytics. We have introduced the frequency and recency patterns that add also to the weight. And we have this whole new formula to compute this match score that gives us the likelihood that this sign-in comes from the user. And now we also have found a way to turn that match score into risk levels that give us the probability for each risk level of the user actually being compromised based on empirical data. So now we have a much better system for compromise detection that it still happen in real time, but now it will feed the adaptive auth engine different risk levels, high, medium, or low, so organizations can go and set up their own threshold for MFA or block or allow based on how tolerant they are to this risk. So takeaways, offline detections, they happen too late, they're not good enough. We need to give organizations defenses so bad guys just don't get through the gate. We want to prevent compromise. Then we're using behavior analytics that really help us lower those both error rates. We have a pretty accurate system, and we use this like a really cool match score that gives us confidence on how much we think the user is who they say they are. And finally, we've added this new flexibility, configurability, different risk levels to choose when you're setting your own adaptive authentication engine rules. And with that, I'll just open the floor to questions if there are any. Oh, OK.
This is great for the authentication piece. But once a user's in the system, are you doing anything with the risk scores to control or monitor what the user is doing and potentially block risky behaviors for users with medium or high risk scores?
Sorry, you said once a user is what?
This system, as you displayed it, either blocks or allows the user to get into the system, or stepped up authentication to get into the system. Once the user is in the system, are you doing anything further to monitor and potentially block risky behavior for users who may be at high risk or medium risk?
Yes. So this part that I talked about today was just one algorithm for sign-in risk, but we also have a whole new other system for user risk that takes all this real-time and also offline signals into account and computes a user risk. So you can also set different policies to remediate users at risk. And then we're also doing work to being able to evaluate risk changes within the session, within the relying parties. So sessions could be revoked based on this risk.
You called out a bunch of behaviors, IP address, location, some device identifiers. Many of those are spoofable.
Yes.
Some more trivially than others. So the question is, systems like this, do they just keep the dumb crooks or the opportunistic crooks out? And the sophisticated, persistent hackers that are, whether state actors or others that know what they want, are able to dodge these systems more trivially, right?
So, yeah, that was a really good question. Most of these are not really that easy to spoof. So as you're saying, like, you actually have to be a pretty sophisticated attacker if you want to spoof an IP address. Device identifiers that we use are not just user agents. They come from like cryptographic thing in the device. So in general, we don't use a user agent because it's just way too easy to spoof. But when we've implemented this algorithm to just raise the bar a little bit more, so even if you've spoofed the easy one, which is the location, right, that just doesn't give you a pass. We also look at the other signals of what other things are matching, and we adjust those weights accordingly. But yeah, that's a very good question. Definitely, this is not like the only defense that you can have, but it's generally a pretty good one.
Can you talk a bit about the performance impact you've seen by adding this into the authentication transaction?
So we have seen a decrease mostly in it's hard to tell how much you're gaining in your true positives or your false negatives because those are harder to understand. You don't know what attacks are in the system that you haven't detected. But we have definitely seen like a 35% false positive rate reduction, which is we're pretty happy with.
So I was wondering if you could talk about how this would work for a user population that may only log in once or twice a year.
Oh, that's an excellent question. So that will be a lot harder. You would have to completely adjust your thresholds and the ways. I think it can still work, but then you'll have to persist the data that you have for the user much longer. We are expiring the data every 6 months, but also it can get overridden if there's too much activity. There's only so much length on the activity store. And so you will have to set all your thresholds different. You could still do it, but it will definitely be tougher because this actually really relies on users that are actives, so you know what their behavior is. Yeah.
Hi.
Oh, hi.
When you're building machine learning systems, there's the concept of bias.
Yes.
And I know here we're not building like the criminal justice system or anything like that, but are there any biases for a system like this? And if so, what are the things you're doing to mitigate against those?
So there's no bias. And first of all, this one, even though I love talking about machine learning and building machine learning systems, this one is more like a mathematical formula that we come up with. It's not. It doesn't train. It's mostly based on heuristics, and it's unique per user, right? So we don't do things like, oh, maybe a country has more weight. No country has more weight. It depends on what country you're in, that another country might have more weight if we just haven't seen you there, right? So there's no biases in those senses. There's some bias in terms of creating more false positives. For example, when an authentication doesn't have as many of those features that we can track. If we don't have a device identifier, then we might only be using the location, which then if you are in a mobile network and the cell phone provider, the network provider is routing you, because they do this all the time and drives us crazy, through like a completely different state, then this might generate a false positive. So in reality, the more we move to modern flows and modern authentications and things like that, the system's just going to become more accurate because there's more data that we see. But otherwise, that's basically, there's no other biases. Rajiv again.
Well, I'll just say that I think one interesting example of bias that might be something to look at is the models for usage in Asia, Southeast Asia are typically multiple users to a single device.
Yeah.
And so if you bias against those, then you end up with a set of problems. So it's fairly common, for example, in China, to use a single phone as a point-of-sale device with 5 plugs in the store page.
Yeah.
And that's very common. Home devices typically are shared more capably. So you're likely to see multiple people come to the same.
Yeah, definitely. This algorithm doesn't make sense. Doesn't make use of seeing multiple users in a device as a signal. It just makes use of, if I have seen you in this device before, that gives me good confidence. But it doesn't cross-track devices. We do have other detections that actually look at, oh, many users are on the same device as a suspicious thing, so that what you're saying is true. But we also have other ways to figuring out which ones are the false positives, so we try to remove them. Okay.
Excellent. Thank you, Maria. Thank you, everyone, for the questions.
Thank you so much.
I imagine we maybe didn't get to everyone, but there are hospitality suites, and we can be cornered with food and alcohol and all the good things. So enjoy your evening. See you all 10:30 tomorrow here for a wonderful panel.